The time has come for NASA, the world's largest space agency, to speak out about a discovery it still cannot fully explain. An interstellar object known as 3I Atlas is emitting structured pulses of light from deep space, a region where darkness and silence are expected to rule. Scientists say this light appears artificial because no comet or space rock has ever shown such stable and precise brightness. The paradox is that this phenomenon occurs while 3I Atlas is still far from the Sun, completely breaking the familiar rules of space physics. This discovery has sparked a global debate and triggered a worldwide race to observe the object before it disappears from humanity's view. After a long period of quiet research and internal review, NASA finally chose to speak about a discovery that refused to settle into any familiar explanation. For months, the agency had been tracking an interstellar object moving through the outer regions of the solar system, collecting data carefully and avoiding public attention while every possible error was questioned and retested. Only recently did NASA confirm that this object, known as 3I Atlas, was emitting structured pulses of light from deep space, a place where scientists normally expect darkness, silence, and randomness. This announcement was unusual not because space is full of strange objects, but because NASA rarely comments on a signal unless it survives repeated internal challenges and independent verification. What drew immediate concern was not how bright the light appeared, but how it behaved over time, since the pulses repeated with a steady rhythm that refused to drift or weaken. At first, the phenomenon was treated as a technical issue, because distant observations often suffer from interference, calibration limits, or background noise that can briefly imitate meaningful patterns. That explanation faded quickly, as the same pulses appeared again, then again, each time matching the same timing and spacing, even when observed by different instruments in different locations. Once multiple observatories confirmed identical patterns, the possibility of coincidence collapsed, and the discussion shifted from equipment problems to physical behavior. In space, light usually follows simple and messy rules, since asteroids brighten as sunlight strikes uneven surfaces, while comets glow when heat releases gas as they approach the sun. These processes are naturally unstable because rotation, surface texture, and temperature changes cause brightness to rise and fall in irregular ways that never remain perfectly timed. 3I Atlas did not follow this pattern, which immediately raised concern among researchers who expected chaos rather than order. The object began flashing while it was still far from the sun, where heat-driven activity should be weak, uneven, and difficult to sustain for long periods. At such distances, there is not enough solar energy to power clean, repeated pulses, and reflected sunlight should vary as the object changes orientation. Instead, the light from 3I Atlas remained steady, holding its rhythm without obvious distortion, even as the object continued its rapid journey through space. Scientists then examined whether rotation could explain the pattern, since tumbling objects often create repeating light curves as they spin. That idea failed as well, because rotating debris produces irregular brightness changes caused by rough shapes and unpredictable motion. The data from 3I Atlas showed none of this behavior, as each pulse arrived with nearly identical timing and structure, suggesting stability rather than chance. Another explanation focused on plasma interactions and solar wind effects, which can generate brief flashes in deep space under certain conditions. Those signals are typically noisy, short-lived, and inconsistent, yet the pulses from 3I Atlas remained intact across different wavelengths and long observation windows. With each familiar mechanism removed, the remaining pattern became harder to dismiss. NASA was left facing a rare situation where no single natural process could explain all the observed behavior at once. Describing the light as artificial did not mean claiming intelligence or intention, but it acknowledged that the behavior appeared structured, repeatable, and internally driven. In scientific terms, artificial describes organization, not awareness, since machines can operate long after their creators are gone. This distinction mattered deeply because it challenged the long-held assumption that interstellar objects are nothing more than silent debris drifting without purpose. For the first time, one of these visitors appeared to behave like something designed to function, even if its original purpose remains unknown. That realization forced NASA to move from silence to transparency because ignoring such a contradiction would only deepen confusion rather than resolve it. If the light from 3I Atlas is not natural, then the object itself demands a closer look, and the next question becomes unavoidable. What else about this visitor have we misunderstood? And what might the data reveal once we stop asking how it shines and begin asking why? What made the case of 3I Atlas impossible to dismiss was not a single strange detail, but a growing list of facts that held up under scrutiny. NASA began by confirming that the light was detected across multiple wavelengths, which meant it was not a visual trick created by one specific sensor or camera setting. Signals appeared in optical data, then showed consistent behavior when examined through different filters and observation modes. This immediately ruled out the idea that scientists were chasing a ghost caused by limited instruments or software artifacts. The agency also made it clear that the pulses were not the result of random glitches, because the same timing pattern appeared repeatedly over long periods of observation. Each detection matched earlier readings with almost no drift, even when the object's position relative to Earth had changed. Independent observatories confirmed the same structure, which removed the possibility of a single faulty system influencing the result. Another concern involved artificial objects created by humans, since satellites and space debris can sometimes reflect light in unexpected ways. NASA addressed this directly by comparing the object's trajectory and speed with every known catalog of Earth-made objects. Nothing matched. The velocity was far too high, and the path through space followed a hyperbolic trajectory that clearly placed the object outside the solar system's origin. This confirmation was critical because it closed the door on one of the most common explanations used to calm early speculation. The timing of the light pulses raised even more questions. NASA confirmed that the intervals between flashes followed clear mathematical ratios rather than drifting randomly over time. Natural processes tend to wobble, stretch, or compress as conditions change. These pulses did not. They arrived with a consistency that suggested an internal process rather than an external influence. Alongside the light, scientists also detected faint but persistent thermal signatures coming from the object. These heat traces were weak, yet they remained stable instead of fading in and out with sunlight exposure. That behavior mattered because passive heating usually rises and falls as an object moves closer or farther from the sun. In this case, the heat signal showed signs of regulation rather than simple absorption. NASA also confirmed subtle changes in motion that could not be ignored. The object did not suddenly accelerate or make sharp turns, but small variations appeared in its speed and orientation. These shifts were too minor to be described as propulsion, yet they did not fully match random gravitational effects either. Scientists described them as deviations that sat in an uncomfortable middle ground between chance and control. Individually, none of these observations would have caused alarm. Astronomy is full of odd readings that later find simple explanations. The problem was that every piece of data pointed in the same direction. The light was structured. The timing was stable. The heat was persistent. The motion was not entirely random. Together, they formed a pattern that resisted being broken apart. NASA emphasized that these findings were not presented as proof of technology, but as confirmed measurements that current models could not fully explain. This distinction was important because science advances by separating what is known from what is guessed. What is known is that the data survived repeated checks, independent confirmation, and careful comparison with known phenomena. What remains unknown is the mechanism behind it all. This is where certainty ends and deeper investigation begins. If the data itself is solid, then the next challenge is understanding behavior rather than questioning detection. That shift in focus marks a turning point. Once scientists stop arguing about whether something is real, they begin asking what kind of system could produce it. Instead of questioning the data itself, scientists began shifting their attention toward how the object was behaving over time. What emerged was a pattern that looked less like random physics and more like a system responding to its environment, a realization that pushed the discussion into far more unsettling territory. What began as a discussion about unusual light slowly turned into a deeper debate about behavior, because patterns only matter when they persist and react. In space science, organized behavior does not mean intelligence, but it does imply structure, layered processes, and responses that follow internal rules rather than random forces. As researchers watched 3I Atlas over longer periods, they noticed that the main light pulses were not acting alone. Fainter secondary flashes appeared within the primary rhythm, almost woven into it, creating a layered signal instead of a single repeated burst. This detail mattered because simple natural sources tend to produce one dominant effect rather than multiple coordinated cycles. These secondary pulses did not drift freely or collapse into noise, but instead maintained their own timing while remaining linked to the main pattern. At the same time, thermal readings revealed something equally puzzling. The object's heat levels rose and fell according to an internal cycle, rather than changing smoothly with distance from the sun. This suggested that whatever was producing the warmth was not purely passive, but regulated in some way that resisted environmental chaos. Such behavior is difficult to explain with exposed rock or ice, which normally reacts directly to external energy without delay or control. Motion data added another layer to the mystery. Instead of tumbling unpredictably like most interstellar debris, 3I Atlas showed long periods of rotational stability. These calm phases were interrupted by subtle adjustments, small corrections that brought the object back into alignment. The changes were too gentle to be called propulsion, yet too precise to be dismissed as coincidence. In known natural objects, rotation usually degrades over time rather than correcting itself. The light also appeared to respond to changes in the surrounding environment. When solar wind conditions shifted, the pulses adjusted slightly in duration and intensity, as if reacting to external pressure rather than ignoring it. Natural flashes caused by plasma interactions tend to break apart under such conditions, but this signal adapted without losing its structure. This adaptability was one of the most troubling aspects for researchers because it suggested feedback rather than randomness. No single observation crossed the line into proof of technology. What unsettled scientists was how these traits reinforced one another. Layered light pulses suggested multiple processes operating together. Thermal cycles hinted at internal regulation. Rotational stability pointed toward balance rather than decay. Environmental response implied awareness of conditions, even if automatic. Each feature alone could perhaps be explained away. Together they formed a profile that did not resemble a lifeless fragment drifting through space. This forced scientists into uncomfortable territory. If the object was not acting randomly, then calling it inert became increasingly difficult. At the same time, caution remained essential. Organized behavior does not require intention, and complex systems can persist long after their creators are gone. Ancient machines, natural self-regulating structures, or processes not yet understood could still fit within the data. What changed was the tone of the conversation. The focus moved away from asking whether something strange was happening and toward understanding how such coordination could exist at all. This shift marked a critical moment in the investigation. Once behavior appears organized, explanations must expand beyond simple physics and into systems thinking. That realization prepared the ground for the next stage of the debate, where scientists began weighing explanations that range from conservative to deeply unsettling. As evidence accumulated, scientists moved carefully toward explanation, because extraordinary behavior demands restraint as much as curiosity. The most conservative view held that the light in motion could still come from a natural mechanism not yet understood, possibly involving unfamiliar materials or interactions that only appear under interstellar conditions. Space has surprised science before, and history offers many examples where unknown physics later became ordinary once better data arrived. This position argued for patience, reminding the community that rarity alone does not equal design. A second line of thinking occupied the middle ground and drew more attention as observations continued. In this view, 3I Atlas might be a very old structure whose original function no longer exists, yet whose internal processes still run automatically. The object would not be active in a purposeful sense, but persistent in the way abandoned machines can keep operating long after their creators are gone. Such systems can repeat cycles, regulate heat, and maintain balance without awareness or decision-making. This explanation fit the idea of layered signals and internal timing without requiring a living presence. The most unsettling hypothesis explored the possibility that the object represents technological debris, a fragment of machinery launched millions of years ago and left to drift between stars. In this scenario, the light pulses are not messages but operational signals, similar to status indicators or energy regulation cycles. The object would not be observing or communicating, but simply functioning according to ancient design rules that still remain intact. Supporters of this view pointed out that technology does not need intelligence to operate, only structure and durability. However, researchers were careful to draw a clear boundary. There is no evidence that a living intelligence is currently controlling the object. No signal carries clear information. No movement suggests active navigation toward targets. The behavior shows regulation, not intention. This distinction matters because speculation can quickly outrun evidence. NASA and independent scientists emphasize that their role was to describe what the data shows, not to decide what it must mean. Each hypothesis faced limits and contradictions. Natural explanations struggle to account for long-term stability across changing environments. The automated structure idea fits some features but raises questions about materials and longevity. Technological debris explains organization but introduces assumptions about ancient engineering that cannot yet be tested. Rather than choosing a single answer, the scientific community accepted uncertainty as the most honest position. NASA reinforced this approach by releasing measurements without dramatic interpretation, allowing researchers worldwide to test ideas independently. This openness prevented the discussion from collapsing into belief or denial. It also highlighted how rare the situation truly is. Few discoveries force scientists to balance so many plausible explanations without clear elimination. What mattered most was not which theory would win, but what each possibility implied for science itself. If the cause is natural, physics must expand. If the cause is mechanical, the universe has a deeper history of construction than assumed. Either outcome reshapes how humanity understands interstellar space. By the end of this phase, one conclusion was shared across all camps. The object was not dangerous, but it was transformative. Its behavior challenged comfortable categories and pushed scientific thinking beyond familiar boundaries. With theory no longer confined to textbooks, attention began shifting toward broader consequences. The question was no longer how to explain the object alone, but how its existence changes the way humanity searches for meaning in the universe. For decades, the search for life beyond Earth followed a familiar path: because scientists focused on biology as the main sign that something living might exist elsewhere. Researchers searched for water, oxygen, methane, and chemical imbalances that could not survive without biological activity. This approach made sense because biology is the only form of life humanity understands with certainty. However, the behavior of 3I Atlas has begun to reveal a major limitation in that strategy. Life does not need to be present for technology to exist. Machines can survive far longer than their creators, especially if they are designed to operate autonomously in hostile environments. This realization is quietly reshaping how scientists define evidence in the search beyond Earth. Instead of focusing only on living systems, attention is shifting toward traces of technology. These traces are known as technosignatures, and artificial light is one of the clearest examples. Natural light in space is usually unstable and irregular, while artificial light tends to show structure, repetition, and control. When such light appears far from stars or strong energy sources, it becomes much harder to explain away. 3I Atlas did not simply glow. It emitted light that behaved consistently over time, across changing conditions and across different observation systems. That behavior forced scientists to reconsider a long-held assumption. Biology may not be the first sign worth noticing. Technology may leave clearer fingerprints than life itself. This shift also raised uncomfortable questions about the past. If instruments were not designed to detect structured behavior, then similar objects may have passed through the solar system unnoticed. Earlier interstellar visitors were analyzed mainly for composition, speed, and origin. Patterns that did not fit those categories may have been dismissed as noise or coincidence. Only now are researchers realizing how much information can be lost through expectation alone. Recognizing technology requires different tools than recognizing life. It demands long-term monitoring instead of brief snapshots. It requires timing analysis rather than chemical focus. It depends on algorithms trained to notice repetition rather than rarity. As a result, observation strategies are beginning to change. Scientists are placing greater value on continuous tracking instead of isolated measurements. They are comparing behavior across multiple wavelengths rather than trusting a single data stream. This method improves the chance of detecting systems that operate quietly instead of violently. Another consequence involves planetary defense and space awareness. 3I Atlas is not considered a threat, yet its behavior shows that interstellar objects can be more complex than previously assumed. If objects can carry structure, then monitoring them becomes more than a safety task. It becomes an effort to understand what enters the solar system at all. This pushes agencies to strengthen early detection networks and expand global cooperation. The goal is not fear, but awareness and preparedness. Beyond science, 3I Atlas has also shifted the emotional meaning of discovery. For many people, life elsewhere has always meant living beings. This case suggests a quieter and more unsettling possibility. The galaxy may be filled with remnants, systems, and machines left behind by civilizations that no longer exist. These objects may never communicate or arrive with spectacle. They may simply pass through, carrying silent evidence that intelligence once shaped matter far beyond Earth. That idea changes humanity's sense of time and place. Life may be rare and brief. Technology may be what truly travels between stars. 3I Atlas does not promise contact, and it does not threaten Earth. What it offers instead is perspective. It suggests that the universe preserves history in motion, light, and structure. And once that perspective takes hold, the search for life becomes something broader. It becomes a search for traces of intelligence written across the vast distances of space. Once the nature of the signal became impossible to ignore, attention quickly moved beyond any single agency. 3I Atlas was traveling fast, and every hour of observation mattered more than the last. Interstellar objects do not wait, and once they leave the inner solar system, their data is gone forever. This urgency triggered a quiet but intense global race to collect as much information as possible before the window closed. NASA focused on long-duration tracking and behavior modeling, using its deep space assets to monitor changes over time rather than isolated moments. The goal was not dramatic discovery, but continuity, because patterns only emerge when signals are followed without interruption. In Europe, space agencies placed their strength in coordination, combining observatories across multiple countries to widen coverage and reduce blind spots. This network approach allowed scientists to compare data across locations, increasing confidence in subtle findings. Asian space agencies expanded independent observation efforts, relying on regional telescopes and rapid data sharing to confirm timing and structure. Instead of competing for headlines, these groups competed for precision. Resolution mattered more than interpretation. Time coverage mattered more than speed. The race was not about who spoke first, but who measured best. Private organizations also entered the picture. Commercial satellites and privately funded observatories provided flexible observation schedules that government systems could not always match. Some companies focused on raw data collection, while others specialized in independent analysis, offering alternative views of the same signals. This diversity added resilience to the investigation. If one system failed, another could confirm or challenge the result. Universities and research institutions played a critical role as well. Academic teams ran continuous monitoring sessions and tested new algorithms designed to detect structured repetition rather than brightness alone. Amateur astronomers also contributed, extending observation time with smaller instruments and helping verify consistency over longer periods. This broad participation created something rare in space science: a shared effort that crossed national, institutional, and professional boundaries. The result was not consensus, but clarity. Data became harder to dismiss and easier to compare. Most importantly, a precedent was set. Humanity now has a model for how to respond when an interstellar object behaves in unexpected ways. Not with panic, not with secrecy, but with coordinated attention. 3i Atlas may leave without answers, but it has already changed how the world observes the unknown. And that shift may matter far more than whatever this object turns out to be. The impact of 3i Atlas did not stop at scientific debate, because it arrived at a time when global space agencies were already upgrading how they watch the sky. At NASA, recent investments focus on early detection and anomaly tracking. Programs like the Near-Earth Object Surveyor and new data processing systems for the James Webb Space Telescope are designed to catch faint, repeating signals that older algorithms often ignored. NASA has also expanded the use of machine learning to flag patterns that do not fit known natural behavior. In Europe, the European Space Agency is strengthening cooperation between space telescopes and ground observatories. ESA has increased funding for long-duration spectral monitoring, allowing scientists to follow subtle changes in light and heat as objects move across the solar system. Shared data platforms now let multiple countries track the same target without interruption. China is moving quickly as well. The China National Space Administration has expanded its deep space surveillance network, placing emphasis on high-frequency optical observation that can capture rapid or structured light behavior. Meanwhile, the Japan Aerospace Exploration Agency is building on its precision science heritage. Drawing from missions like Hayabusa, Japan is investing in sensors that can detect tiny changes in rotation, heat, and reflectivity over long periods. Together, these efforts mark a turning point in how humanity watches the sky. The next interstellar object will not just be detected earlier, but studied with the awareness that even the smallest anomaly could matter. As 3i Atlas moves away, it leaves behind more than fading light. It forces science to rethink how interstellar objects are seen, measured, and understood. This was not a warning and not a message, but it was a signal that assumptions can break quietly. Whether natural or artificial, 3i Atlas changed how humanity watches the universe.